Hello again, physics friends. Today we are going to focus on the shapes of gravitational orbits. And if you recall, we started this journey by thinking about central forces, and we found that for central forces, we have an equation of motion for the coordinate r that's given by the r derivative of some effective potential, where this effective potential includes a term that depends on the angular momentum, L naught, and also a term that depends on the interaction potential for the two-body question of interest. In this case, we're going to focus specifically on Newtonian gravity, and in Newtonian gravity, we have a very specific potential. The potential is minus gmm over r. It's a 1 over r potential. And what we found in the last video is if you take this equation of motion, the second order differential equation of r with respect to time, and you change using the chain rule, you change the derivatives from time derivatives to spatial derivatives, then you find a shape of the orbit. And the shape of the orbit that we found for a gravitational orbit specifically is the following. The distance from the origin depends on the angle in the following way. C is a constant, and specifically that constant depends on the angular momentum, and this gamma term, gmm, and mu is the reduced mass. The other constant is epsilon, and epsilon is also a positive constant, and it's undetermined for now. It will depend on the initial conditions of the system. So our goal for today is to take this equation for the shape of the orbit, and we want to study the different cases. And specifically, we're going to look at different values for epsilon, and the different values for epsilon give us different kinds of orbital shapes. And what we're going to find is that those orbital shapes are conical sections or conic sections, and they are ellipses or parabolas or hyperbole. And we'll talk about each of those in turn. Okay, we moved all of this work to the side, and we're going to step through in 3 different cases. The first is case 1, where epsilon is less than 1. We're going to see that those lead to bound orbits. Cases 2 and 3 will be epsilon equal to 1 and epsilon greater than 1. What we can see from the shape of the orbit, the equation of the orbit, the reason that we break up epsilon into the cases of bigger than or less than 1 or equal to 1 is whether or not this denominator can be 0. In other words, whether or not r can get arbitrarily large, go to infinity. So we know that cosine is bound. It cannot be smaller than minus 1. It cannot be bigger than plus 1. So we could have the denominator equal 0 if epsilon were 1 or bigger, because when epsilon is 1 or bigger, you can choose an angle phi such that epsilon cosine phi equals minus 1 and the denominator equals 0 and r goes to infinity. Okay, so we're going to start with a discussion for epsilon less than 1, in which case the denominator can never get to 0. And we're going to break this case up into 2. We'll start with case 1a, in which epsilon is equal to 0. And this case doesn't take that long to discuss, because if epsilon is equal to 0, then the denominator is just 1, and the whole right-hand side is just equal to c, a constant. That tells you that r is a constant independent of angle. Okay, so the two bodies are always the same distance apart. These correspond to circular orbits. At constant separation. So before going on, I want to make the connection between the shape of the orbit and the energy of the system. So if you recall, we can write down in 2D polar the energy of a system as kinetic plus potential, which is mu over 2 v squared in polar plus the potential. But notice this term, in the second term, the angular piece here that involves the phi double dot, gets combined with the potential to form mu effective. And so we can think of the total energy as just the radial piece, just the r dot term, plus U effective. Okay, so those two blue terms are now merged into U effective by itself. So what this means is, even though this is a two-dimensional problem, we can draw the U effective and we can think about different orbits just graphically. So if we recall, the gravitational potential is a minus 1 over r potential. The centrifugal potential is a 1 over r squared, and so we end up with something like this. So we have here a plot of the centrifugal 1 over r squared potential. We have here the minus 1 over r potential for gravity, and when we add them together, we get the effective potential. So what does this mean? Case 1a, epsilon equals 0, r equals a constant c. Well, that corresponds to the situation where the particle sits at a single r coordinate. Okay, and it does not grow or shrink. Okay, so we have a two-body system, which in general could have two different shape masses. And what we're saying here is that the separation between them is constant. Okay, so the two could be in orbit about each other, about their common center of mass, but when epsilon equals 0, that corresponds to the case where there's no radial kinetic energy. In other words, the total energy of the system, if we think of that as a red line here, I'll tell that the total energy for case 1a, that the total energy is simply equal to the effective potential, black equals red, which tells us that r dot is 0, and of course we see that r dot is 0 because r is a constant. So there's no radial velocity. The two masses are always the same distance apart. All right. So the particle just sits at a single separation r as these objects orbit around each other. Okay, so we're tidying up, we're moving things around a little bit. We'll keep this reference to our energy here, and we'll keep our diagram, and we'll move on to case 1b. And in case 1b, we're going to have epsilon bigger than 0 but less than 1. And this is still the bound orbit scenario. We're still in the case where epsilon is less than 1. So what that means is we're going to have a minimum r and a maximum r. And let's see how that plays out. The minimum r is going to come when cosine phi is the biggest, so that we divide by the biggest number. So the biggest cosine phi can get is plus 1. So we'll have minimum r equal to r when phi is equal to 0. That corresponds to when cosine is 1, and that expression will evaluate to c over 1 plus epsilon. And we'll have a maximum r when the denominator is a minimum, and that's when phi is equal to pi, 180 degrees, in which cosine is minus 1, so we'll have a c over 1 minus epsilon. And further, we see that after 2 pi, this function r of phi returns back to where it was at r of 0. So r of phi is periodic in 2 pi. In other words, r of 0 is the same as r of 2 pi, or more generally, r of any angle is the same as that angle plus 2 pi. Which means this orbit will repeat and repeat and repeat and repeat and repeat. So let's look at this r min and r max. Okay, we have these two values. One's going to be a minimum radius, and one's going to be a maximum radius. Okay, and so we can see at those two positions, r dot will be 0. The total energy of the system will just equal to the effective potential. So I'll call this the energy associated with case 1b. Okay, and so what we see is that generally there's going to be some kinetic energy because the effective potential is less than the red line in this region. So the particle will have a radial, not component, but a contribution to the kinetic energy will come from the change of r. Mu over 2 r dot squared will be non-zero in this region. But when at these two green points, the turning points, mu over 2 r dot squared will be 0, and the energy for that case 1b will be equal to the effective potential. Those are your turning points in radius. Okay, so what we're going to find is that we have a minimum radius, we have a maximum radius, and this is going to correspond to an elliptical orbit. And you'll be able to rewrite the equation of the orbit as in Cartesian coordinates in the following way. Okay. And here, this term A is defined to be the constant c over 1 minus epsilon squared, where the constant B is defined to be c over root 1 minus epsilon squared. And this constant D is equal to A times epsilon. Okay. So this is the equation of an ellipse that has a major axis and a minor axis. And we can think of having one object at a focus of the ellipse and the other one on the ellipse. And we know that when phi equals 0, which corresponds to this line here, you have the minimum approach. And when phi equals pi, which corresponds to this point here, you have the furthest approach between these two particles. And in general, you're somewhere in between. So this is the angle phi. And we can represent graphically the variables A, B, and D. A is given by this semi-major axis, so it's half, if in this orientation, half the width of the ellipse, excuse me. B is half the height of the ellipse, semi-major axis, and semi-minor axes. Here we have our min. And here we have our max. Like so. And what else can we say? Well, when phi, up here in the right corner, when phi is equal to 90 degrees, cosine phi is 0. So when phi is 90 degrees, r equals to c. So this height right here, when phi would be 90 degrees, is equal to c. So that's a graphical representation of all of the constants in the equation for the ellipse. And now we're ready to interpret this quantity epsilon. Okay, if we look at the ratio of A over B, that's the ratio of the width to the height of this ellipse, or the major to minor axis. That ratio is equal to square root of 1 minus epsilon squared. And this is a definition of the eccentricity of the ellipse. Okay, so it's a measure of how non-circular this ellipse is. Notice if A equals to B, then you have a circle, and that must mean that A over B is 1, so that means epsilon is 0. So epsilon equals 0 is a circle. We already saw that. And as long as epsilon is less than 1, this quantity on the right-hand side remains real. And we have an ellipse. So small epsilon close to 0 would be a circular shape, and a large epsilon that's less than 1 but approaching 1 would have a very non-circular ellipse, a highly eccentric ellipse. Okay, so we call this the eccentricity of the ellipse. So I've shuffled things around here just to keep the key ideas that we'll need: the shape of the ellipse, an expression for the energy, and now we have this effective potential graph. We have two possible energies for the system. The lowest energy here corresponds to a circular orbit. The next energy I've listed here corresponds to an elliptical orbit, and that energy could be anywhere that's bigger than the circular orbit case. So it could be down here, it could be here, it could be here, it could be here, and so on. In all of those cases, you'll have a turning point on both the left and the right sides. And that continues on until you reach a total energy of 0. At a total energy of 0, U effective, remember, is going to approach 0 from below, never reaching 0 though. So if your energy is exactly 0, then you'll have a turning point on the left side for minimum R, but you will not have a turning point on the maximum side of R. So what that tells us is that the orbit consists of a closest approach, but then zooming out to infinity from there. So we can talk about this now. That's the case of epsilon equaling 1, so that we can get 0 in the denominator. And as I mentioned just now, that corresponds to a total energy of the system, capital E, of 0, like this. So our equation of the orbit, R of phi, is a constant over 1 plus cosine of phi. And notice that when phi is equal to pi, then cosine of pi is minus 1, so the denominator is 0. And R gets arbitrarily large. The same is true when phi is equal to minus pi. Everything here holds. And so we have a situation where we're going to have a minimum approach, and that's when cosine phi is 1. So we have c over 1 plus 1, or c over 2. But then there's no maximum, there's no R max. We're going to have an R min, but no R max. Okay, so the other interesting angle is when phi is equal to 0. We have R of 0 is equal to c over 1 plus 1, or c over 2. And this is corresponding to R min in the case of the eccentricity equaling 1. So here's a graphical representation of that. When phi is equal to 0, R of 0 is c over 2, that's R min right here. And then as phi gets bigger and bigger and bigger, R gets bigger and bigger and bigger. And eventually as phi grows to be pi, R goes to infinity. So we have this parabolic orbit. And specifically, it's unbound, meaning that there's an R min, but there's no R max, or rather, R max is infinity. You can show that this expression for position versus angle can be recast in Cartesian coordinates as the equation of a parabola. Like so. And if you thought the equation of the parabola should be y being proportional to x squared, or at least y a function of x squared, notice that that would give you a parabola that is kind of oriented up or down on the page, but the way we've defined it, our phi angle, we have a parabola that opens up left or right. In this case, opens up to the left, so it's really x is a function of y squared. We can then annotate our energy diagram to show what energy you need for this case, case 2, and that is an energy of 0. Okay, an energy of 0, you do not have a turning point on the right side, so R max is infinite, but you will have a turning point on the left side. You'll have an R min, which is c over 2. And notice it's kind of represented here. If the circular orbit scale is c, we go about halfway towards the origin, and that's c over 2. The final case to discuss is the only remaining option, which is epsilon bigger than 1. So we'll get to that next. Okay, so again, third case, epsilon bigger than 1. That corresponds to an energy that's positive. Could be anywhere here above the x-axis. Okay, and this solution shares a lot with the parabolic solution. So E3 is an energy that's bigger than 0. This, it turns out, will correspond to a hyperbola. And we'll see what that means. Right, so remember, our equation for the orbit is c over 1 plus epsilon cosine of phi. But now epsilon is bigger than 1, so we can make the denominator small. We can make the denominator equal to 0 before phi gets to pi or minus pi. Okay, so we can, there's some phi max at which epsilon cosine phi plus 1 is equal to 0, and that makes r go to infinity. So if we think about this problem graphically, we have, as before, our two masses. We'll have a closest approach. Like so. And we've defined our angle phi, same as before. Okay. And so we still have r at 0, phi equals 0, is still c over 1 plus epsilon. So that's our r min. Okay. But now there's going to be some angle phi max and when you approach that angle phi max, r approaches infinity. So this curve will asymptotically approach this line, the blue dashed line, and that is a hyperbola. That's the case of epsilon bigger than 1. These special angles plus or minus phi max, those are the ones that correspond to when 1 plus epsilon cosine of phi max is equal to 0, so that the denominator is 0 and r blows up. So you can define cosine max from that. You can say epsilon times cosine of phi max is equal to minus 1. You could continue to solve for phi max directly, but it doesn't give you much information beyond that. So what do we learn? We know that as long as, or the angle phi is restricted to live between minus and plus phi max, so you can never get the particle over here in this direction. The particle is going to be restricted to be in this regime from here to here. The equation of the hyperbola looks like this: x minus a constant squared over another constant squared minus y squared over another constant squared equals 1. Here, with the ellipse, we had a, b, and d, and here I'm using the Greek equivalents alpha, beta, and delta, if you like. And you can show that this is indeed true, that you can re-express c over 1 plus epsilon cosine phi in the following way. So here's then a summary of the cases we described. We have two bound orbits, a circle and an ellipse. We called that case 1a and case 1b. We have a parabola for which the energy is 0, and then we have a hyperbola for which the energy is bigger than 0. So we can annotate this diagram. We can say for both the circle and the ellipse, the energy is less than 0. For the parabola, the energy is equal to 0, and for the hyperbola, the energy is bigger than 0. For the ellipse and the circle, the motion is bound. For the parabola and the hyperbola, the motion is unbound. So, right, it's unbound because the separation between the objects grows without limit in both the hyperbola and the parabola, but the separation between the two bodies is limited for the circle and the ellipse. And in the case of the circle, that separation is constant. So I'll leave you with a couple other expressions, right? You might assume or you might infer that there's a relationship between epsilon and energy. There seem to be these three regimes, right? Epsilon between 0 and 1 corresponds to a negative energy. Epsilon equal to 1 corresponds to 0 energy. Epsilon bigger than 1 corresponds to energy bigger than 0. And indeed, this is the relationship between energy and epsilon, shown here. Energy is a calculable function of epsilon, where epsilon is the eccentricity of the orbit. So that's something to just make sure we're aware of. And the final thing is I'll just put in a summary table that summarizes the relationship between eccentricity, energy, and the orbital shape. And this table, again, is from Taylor. We have values, different ranges for the eccentricity. The first two rows correspond to bound orbits. Eccentricity is less than 1 in both of those cases. And then we have the two unbound orbits, the parabola and the hyperbola. So planets are orbiting on bound orbits like ellipses, but you could have a visitor to the solar system, right, that enters from infinity, does a close pass to the sun, and then exits back to infinity again. That would be an unbound orbit, whereas all the planets that are periodic in their orbits about the sun would be in these bound orbits that are in general ellipses and occasionally get quite close to circular. All right, well, that's it for now. Until next time, take care and be well.